Hello everyone. So today we are going to discuss some numerical problems on module 2. So let us check the question. A retaining wall 6 meter high retains dry sand with an angle of friction of 30 degree and unit weight of 16.2 kilonewton per meter cube. Determine the earth pressure at rest. If the water table rises to the top of the wall, determine the increase in the thrust on the wall. Assume the submerged unit weight of the sand as 10 kilonewton per meter cube. So in this question, you are asked to find out the earth pressure at rest. And there are both cases, that is first without the water table and next if the water table rises to the top of the wall, you have to find out what will be the increase in the pressure. So let us check what are the data given. So you are given the bulk unit weight as 16.2 kilonewton per meter cube and the angle of internal friction as 30 degree and the height of the wall as 6 meter and the submerged unit weight as 10 kilonewton per meter cube. So as the first step, you have to first find out the earth pressure coefficient at rest, and for that you have to use the formula as 1 minus sine phi, and phi is the angle of internal friction and which is given as 30 degree. So substituting as 30 degree, the active, the earth pressure coefficient at rest is 0.5. And in the first case, there is no water table given. So using the formula for the earth pressure at rest, which is given by Ko into gamma into H, where gamma is the bulk unit weight and H is the height of the retaining wall. Substituting the corresponding values for that, we will be getting the earth pressure at rest as 48.6 kilonewton per meter square. And you are asked to find out the force. What will be the force acting on the retaining wall? And you have to find out the area of this pressure distribution diagram. And for that, use the 1 by 2 into 48.6 into 6. And the force acting at rest will be on 45.8 kilonewton. Now coming to the second case, that is you are given the water table and which is at the top of the wall and the whole soil will be in the submerged condition and you are given the submerged unit weight as 10 kilonewton per meter cube, and so the total lateral thrust will be the sum of the effective as well as the neutral lateral thrust. So first of all, the effective lateral thrust will be, that is using the submerged unit weight as gamma, and the value of coefficient of earth pressure at rest will be 0.5 itself. The bulk unit weight will be replaced by the submerged unit weight, which is 10, and the height of the retaining wall is 6 itself. So substituting these values, we will be getting 90 kilonewton per meter run. And due to this water table, the pressure will be 1 by 2 into unit weight of water, that is gamma W unit weight of water, which is taken as 10 itself, and H is a water table height, which is the height of the retaining wall itself, as the water table is at the top of the wall. So substituting all these values, the force due to the water table will be 180 kilonewton per meter run, and the sum of these two will be the total lateral thrust, which will be 180 plus 90, which is 270 kilonewton per meter run. So the increase in the thrust after the water table is present will be this 124.2 kilonewton per meter run. That is the value which is got by subtracting the force before the water table is present and as well as the when the water table is present, and when we subtract those two forces, we will be getting the increase in the thrust. Now coming to the second problem, it is a gravity retaining wall retains 12 meters of a backfill and the bulk unit weight is 17.7 kilonewton per meter cube and the angle of internal friction is 25 degree with a uniform horizontal surface. Assume the wall interface to be vertical. Determine the magnitude and point of application of the total active pressure If the water table is at a height of 6 meter, how far do the magnitude and the point of application of active pressure change? So in this also, you have to calculate both the cases, that is before the water table is present and after the water table is present. And in this case, you have to calculate the active force. So what are all the data is given? You are given the bulk unit weight as 17.7 kilonewton per meter cube, angle of internal friction as 25 degree, and height of the retaining wall as 12 meter. And in case if the water table is present, that is if you are taking the second case, the water table is located at 6 meter, and you have to calculate the active pressure and the active force acting on the retaining wall. So first of all, you have to calculate the active earth pressure coefficient, which is given by the equation 1 minus sine phi by 1 plus sine phi, where phi is the angle of internal friction, which is given as 25 degree here, and substituting in those values, we will be getting the active earth pressure coefficient as 0.406. And in the first case, you have to find out the active force when the water table is not present. So you just have to draw first the pressure distribution diagram for the corresponding active pressure, and which is given by the base of the triangle value will be given by the Ka into gamma into H, where gamma is the bulk unit weight, that is when the if there is no water table is present, so which is 17.7 kilonewton per meter cube, and H is the height of the retaining wall. And substituting these values, we will be getting the active earth pressure, and which is given by 86.2 kilonewton per meter square. After doing after drawing this pressure distribution diagram, that is as the base of this triangle value as Ka gamma H, and after that, in order to find the active force, we have to find the area of this pressure distribution diagram, and the area of the triangle is half BH, and therefore 1 by 2 half 1 by 2 into gamma H square into Ka will be the force, active force acting on the retaining wall, and substituting the corresponding values, that is we have to find out the area of this pressure distribution diagram. So the area of the pressure distribution diagram after substituting the values will be, that is 1 by 2 into 12 into 86.2 will be 517.2 kilonewton. This will be the active force acting on the retaining wall in the absence of the water table. Just you have to substitute the values for this active pressure, that is which is given by Ka gamma H, which will be the base of this pressure distribution diagram. And coming to the next, that is if the water table is located and the location of the water table is given as 6 meter from the top or bottom, that is as it is a 12 meter height retaining wall, the 6 meter in the middle of this, the water table is located. And the corresponding pressure distribution diagram, if the water table is located, that is this is a partially submerged case, this will be in this form, that is above the or on the above the top of this water table, there will be the dry soil condition, and you have to draw first of all the pressure acted on this retaining wall by this dry soil, and whose bulk unit weight is 17.7 kilonewton per meter cube. And that pressure distribution diagram has to be extended downward, and that value is given as Ka gamma S2. And then next, you have to draw the pressure acting on the retaining wall due to this submerged soil, that is a soil which is below the water table, and whose submerged unit weight is not given. So you are assuming that the submerged unit weight of the soil is 10 kilonewton per meter cube. And the pressure on the retaining wall due to the submerged soil is given by Ka into gamma dash H1, where gamma dash is the submerged unit weight of the soil, and it is multiplied with the height of this submerged soil state, and it is 6 itself. So H1 is the height of the submerged soil, and H2 is the height of the dry soil. And next you have to consider the pore water pressure, that is the pressure which is acting on the retaining wall by the water only, and which is given by unit weight of the water multiplied with the height of the water. table. And in this way, this will be the pressure distribution diagram if the water table is present at a particular location. That is, if the soil is in the partial submerged case. And after drawing this pressure distribution diagram, you have to find the total force acting on the retaining wall by calculating the area of this pressure distribution diagram. That is, first of all, you have to calculate the pressure due to each of these. First of all, the pressure due to this dry soil only, which is given by the above triangle, that is K into gamma into H2, where H2 is the height of the dry soil only. K is the active earth pressure coefficient. There is no change in the active earth pressure coefficient, and gamma is the unit weight, bulk unit weight, that is weight of the dry soil, and which is extended downward, and the base of this rectangle is also Ka gamma H2. And after that, you are drawing this pressure distribution diagram for the submerged soil condition, and the submerged unit weight is not given, and so it is assumed as 10 kilonewton per meter cube. And substituting in order to find out the pressure due to the submerged soil, Ka into gamma dash into H1, where H1 is the height of the soil of submerged soil. So, which is 6, and you are substituting in those values, and we are getting as 24.4. And then you have to consider the pressure due to the water only, which is got by multiplying the unit weight of water with the height of the water table, and which is 6, and in this way we got 58.9 itself. Now you have to find out the pressure, I mean the force acting on the retaining wall, which is obtained by calculating the area, total area of this pressure distribution diagram. So first you have to find out the area of the first triangle, that is which is shown in the green shade. That is, for that 1 by 2 half BH, where 1 by 2 into base value is 43.1, that which is the pressure, into height of the soil, which is 6, then plus, then you have to consider the rectangular portion in the green shaded portion, and whose area is L into B. So length is 6 into, and the base is 43.1, that is Ka, which is the same as 43.1 itself. Then the next triangle, which is the pressure distribution diagram of the submerged soil, and for that half BH, 1 by 2 into 6 is the height of this soil, and into 24.4, which is the pressure, that is the base of the triangle, plus the another triangle, that is a pressure distribution diagram for the pour water or the water only, and for that 1 by 2 into 6, which is the height of the water table, into the base of the triangle, which is gamma W into H1, 58.9. In this way we are getting the total force acting on the retaining wall. And here we are also asked to find out the point of application of this force, that is where this total force is acting. For that you have to find the moment of each of these forces and find the location of the total force. So for that, first of all, you have to find the location of the force 129.3, that is in the first triangle, that is the top triangle, the 129.3, this force will be acting at a distance of, considering the triangle only, it will be acting at a distance of h by 3. That is, the height is 6, then 6 by 3, that is 2 meter, it will be acting at the top triangle. But when we consider from the base of the retaining wall, the height or the point of application of the force 129.3 will be 6 plus 2, and hence it is 8. Then coming to the next force, that is 258.6, that force will be due to this rectangular portion, and that force will be acting at a location of h by 2 distance. For a rectangular portion, the point of application of the force, the resultant force will be acting at a height of h by 2, so 6 by 2, which will be 3. Hence 258.6 into 3, plus the next force is 73.2, that is next force due to this submerged soil condition, the force 73.2, it is another triangle, and for the triangle, the resultant force will be acting at a location of h by 3, and height here it is 6, so 6 by 3, which is 2, plus the next pore water pressure, and the force is 176.7, and here also the location of the resultant will be h by 3, that is 6 by 3, which is 2. And when we divide that with the total force acting, which is 63 637.8 kilonewton, we will be getting the location of the total force, which is 3.62 meter, and this is marked here. In this way, we are getting the point of application of the total force. And you have also asked to find out the what is the total increase in the force, that is when the water table is not present, and when the water table is present, what will be the increase in the force and what will be the change in the point of application. In this way, we found out the point of application of the force when there is no water table condition, that is it will be at a distance of 4 meter, and after the water table is located, if the water table is located, then the point of application will be getting lowered by a 0.38 meter. In this way, we will be calculating this, what is the change in the pressure, active pressure, as well as in the point of application. The next problems will be discussed in the next video. So thank you.